Dante Certification Program Level 3. Throughout this course, we talk a lot about networking. Dante being a service that runs on a network, it becomes essential for audio professionals to understand what a network is. This module addresses that. A network is a collection of devices that are able to communicate with one another. In our case, a Dante network is a collection of devices that are connected via IP and can exchange audio information with each other. Of course, Dante does much more than just pass audio down a wire. It allows devices to be automatically discovered. Dante devices use human-readable names, both for the device channel and its channel labels. Diagnostic information is made available from the devices to controller applications. And devices and channels can be managed by a systems administrator, and a secure ecosystem can be built. Dante devices exchange information over an IP or Internet Protocol network. At this point, in all other areas of life, the term network has become synonymous to IP network. The biggest single network in the world is the public Internet. Unsurprisingly, this too uses IP. So, does networking mean IP? It's true to say that IP networks are the most common types of network in the world today. But this wasn't always the case. This brings us to ask the question why? Why has IP become the dominant networking technology? There are several reasons. It's supported by the most manufacturers, both in terms of software and hardware. It has been applied to all industries from banking to space rockets to huge science projects. IP is hugely flexible, and by that we mean the network is neutral. We'll talk about the network being neutral in a bit, but basically that means we don't care about what type of data is being sent over an IP network. It could be documents, web pages, streaming audio, phone calls, or video, or whatever else. IP networks scale really well, even to a global scale. Equipment and cabling takes advantage of economies of scale in an unprecedented way. The model IP follows is vastly more scalable than alternatives. It's also understood by millions of engineers and technicians around the world, and it's used by billions of end users every hour of every day. Before IP networks became really big in the telecom industry, we had something called TDM, that is, time division multiplexing. TDM is nice because it's quite easy to understand when you're coming from the analog world where you're manually patching telephone lines into each other like the old telephone switchboard operators did. It's also the method that AES-3, AES-10, AES-50 or MADI used. What it works on is the idea that communication between devices runs on a master clock, and then you subdivide that master clock into slots. Then you put the data into each slot. And as long as the sending end puts the data into the slots that the receiving end could understand, you could pull it back out again. Conceptually, it's quite easy. It's like switching circuits in an old-fashioned telephone exchange. Cables used to be the part and parcel of the communication system under this model. Faster, more expensive cables did high bandwidth tasks, while cheaper, more common cables did the lower bandwidth tasks. As the industry started to evolve within the analog world, people started running into complications. Wiring then became complex. Limitations of distance became more and more apparent. Deployment time started to increase, and this eventually led for the desire to reduce cabling. TDM was used by older digital formats. It runs at a set rate. This is considered a synchronous network. In TDM, as we saw earlier, time slots are filled with data, and as long as the transmitting end puts the right data in the correct time slot, then the outgoing resultant data matches that which went in. The capacity of the network depends on the clock frequency. Unlike IP networks, TDM networks are not neutral. In telecommunications, as long as the traffic was only voice, this was simple. But once they started to provide other services, the TDM model started to show its inefficiencies. Now that we've talked a little bit about TDM, let's take a minute to observe this chart. This chart compares the efficiency of MADI, a digital audio protocol using TDM, to Dante. As you can see, MADI is only efficient at 100% capacity for 64 channels. That is, 1 to 64 channels uses 100% of the bandwidth. If you want to use the 65th channel, it starts the cycle all over again, so you end up doubling your resource requirements unnecessarily. Compared to MADI, which uses TDM, Dante scales much more efficiently because it uses IP. Now, pay attention to the Dante column and compare it to the MADI column. In Dante, with 65 channels, we still have room. Now note that this is all on a 100 megabit per second link. Simply using a 1 gigabit link in this situation gives you so much more space.